Any questions on the...
Dude, you honestly need to go home.
Yes, ma'am.
Number 2 on the Outwood machine. I'm having a problem wrapping my...
Compared to the applied force acting on it?
Or number 3, sorry. I meant
Compared to the net force?
Yeah.
Okay.
They're both like the same quantity.
Well, kind of. Okay, so here's the setup with the Outwood machine. So let's say this is that 220 gram and this is the 200 gram, right? So just to make life simple, we're always going to assume, we're just going to always call the bigger mass the applied force. Okay? Boom. So this is the applied force, and we're going to make this our opposing force. Right? Good with that? Okay. So here's my question. So this is what I want you to look at. Is that if I just cut this string, okay? If I just cut this string, what's going to happen to the acceleration of this 220 gram mass if I cut the string versus if this is attached? Okay?
Because there's no opposing force.
Beautiful. That's it. Now, whether this string is attached or not, is that going to alter the applied force acting on the system?
Yeah.
Whether I cut the string or not, is that going to alter the applied force?
No, because it's the same half.
Yeah. There.
Okay.
Brains
So
wrapped around it now.
What?
Hey guys, look, this is the note Miss Shirts wrote me my freshman year. So
Can you give me an indicator?
It's over.
I kept
Over.
it. It's so cute.
Oh, are you trying to show the camera or
The applied
us?
force?
Oh no.
Okay.
It'll stay the same. 'cause
On
I have
number
mine too in my
11.
wallet.
Yeah.
Find your passion in life. That was her ending.
Yeah.
On number 11,
I hate being
Okay.
by the camera.
so here's the deal. Let's talk about number 11. If you're an engineer, you always plan for like a worst case scenario, okay?
I lost my pencil.
Always plan for a worst case scenario. Like you're always asking, what if this happens? So here's the drill. So you've got an elevator. The elevator itself has a mass of 500 kilograms. Okay? So that's just the elevator itself. Then you figure, okay, what's a worst case scenario? Worst case scenario, there's a fraternity party. The fraternity decides how many guys can we cram into this elevator. So you figure, worst case scenario, we've got 20 drunk fraternity guys in the elevator, each with a mass of 75 kilograms.
Always
Absolute,
drunk.
Yeah.
absolute
Why
worst
would you
case
assume
scenario.
that?
Yeah, why would you assume that?
Yeah, I think I'm
I
gonna.
think they're pretty
I'm
nice.
gonna grab to be in a
Nice.
band of brothers.
There you go.
For brotherhood.
Go with that.
For later life.
Go with that.
Business
I'm
connections later
happy.
in life.
I'm happy for you. Good. Okay, Jeff.
Were you
All
a
right.
frat? That's my brother.
Sober
Were you-
fraternity.
Oh, God, no. Oh, God, no.
You were.
You just
No, no,
I find that
trust
hard to
me.
believe.
My father would have
I
shot
could
me.
see you being
had
a
I joined a
super
fraternity.
partier, like back in college.
Terrible.
Let the camera be
Okay.
noted that he was in the
Like
fraternity. Like Kappa Phi. And that's what you were.
Dear Lord.
I just made that up. I don't know.
Okay. So anyway, so Hunter, you're being particularly not obnoxious today. Stop. So here's the deal. Any cable has a breaking point. Okay? Once you exceed that point, bad things happen. So basically what we're saying is that that cable at maximum can apply a force of 2.96 times 10 to the 4th newtons. Okay? That's your applied force. Okay? Take the mass of the elevator plus the mass of all the people inside, multiply that by G, there's your opposing force. The difference between those two is your net force. Basically find the acceleration. Your acceleration on number 11 should be between 4 and 8.
I feel better about myself.
Should be between 4 and 8.
Oh, yeah. I was thinking 8 and 11.
Now, let's talk about number 12. Here's what you cannot do on number 12. If you just took 4.50 times 10 to the third kilograms and multiplied that by 2 meters per second squared, and that's all you did, that's wrong. Because what else does the helicopter have to overcome? Gravity. So think about this. If this helicopter is just going to hover, at a minimum, I have to apply enough force to overcome the gravitational pull. So that's the minimum amount of force that I have to apply. If I want this thing to accelerate upward, I have to apply even more force than that. So your answer on number 12 has to be greater than the weight of the helicopter itself. It's just like, hey, if you want to lift 100 pounds, okay, at a minimum you have to exert 100 pounds of force. If you want to lift that weight up higher to make it accelerate upwards, you have to apply more than 100 pounds. Okay?
Number 4.
When you're comparing your answers to 13 and 14, some of the answers will be the same. Okay, you should get some of the same answers on 13 and 14. Okay? Not all of them, but some of them should be the same. And on the Atwood machine, when you calculate the theoretical acceleration, both of those accelerations should be between 0.4 and 0.9. So that when you go across, those accelerations, those two accelerations at the end, there in the middle on page 3, should be somewhere between 0.4 and 0.9.
For both of them?
Yes.
Will they not be the same?
No, they're not the same, but I'm just telling you. Both answers should be between 0.4 and 0.9.
Okay, so then how do you find the force applied?
Okay, your force applied is going to be 0.22 kilograms times 9.8 meters per second squared.
Don't you have to add them together? No?
No. So your
What did you
applied
add?
force is just this mass times g.
Okay.
Your opposing force is this mass times g.
I had them ended.
The difference between the two of them is your net force. Divide your net force by the total mass. That's the only time you use the total mass.
You only use the total mass on net force.
Yes.
But those two, you use whatever mass is used on that.
Yeah.
Okay.
Okay. We need a little bit.
Oh, cool. A slight crisis. Yeah. So the only thing that changes on the 240 is that this becomes 240. So this is 0.24 times g. It has the exact same opposing force, but then you're going to divide by a completely different total mass.
I don't know what to erase.
I don't know what to do now.
I might just redo it.
Okay.
I don't know what to.
Make sure on the beginning that you show your work because everybody's data is different. Okay? So on that front page up there at the top, show your work. Everybody's data is different.
So this FNet is not right. None of this is right.
Okay. Anything else? Going once, going twice. So fantastic.
So let's say.
Okay. So here's, there's a couple different setups to kind of look at this whole idea of forces and tension and all this good stuff. So here's what I've got. In this situation, in between here, I have a Newton scale. Okay? It's a 10 Newton scale, maximum reading of 10. On each side of the string, I have the exact same mass suspended, which is a 0.5 kilogram mass. So I have a 0.5 kilogram mass hanging over there. I have a 0.5 kilogram mass hanging on that side. Okay? So that's situation number 1. Situation number 2, I have a, I'll lift this up so the camera can see it. I've got a 0.5 kilogram mass here, a 0.5 kilogram mass here, suspended by a pulley, also hooked up to a 10 Newton scale. Okay? Now, here's the question. you don't get an answer because you've seen what the scale reads. So what's going to be, assuming that the pulley has negligible mass, okay? So what's going to be the reading on that scale?
Numbers.
Numbers, that narrows it down.
4.9.
How come she gets your road coat? I wanted that.
I'm guessing around 10.
Just said around 4.9.
That's because but there's two of them on there.
Yeah, so I've got 2.5 kilogram masses hanging there, right? But it's suspended over a string like this, right? So what's the reading on the scale?
10 newtons.
10 newtons. Why?
Because there's two of them.
That was dumb.
They're both pulling down.
Yeah.
Same force. So what's the combined mass then?
1
kilogram, right?
But it's like 10, because you got a pulley on there too.
Yeah, so it's going to be something around 10, right? Okay, and if you look, right, we're at about 9.9, pretty close to 10 newtons, right? Okay, so this is about 10 newtons. So here's the next question. So I've got a spring scale in between, okay? So basically when I lift that up, you'll see that I've got one string hooked up to the reading on this, and I've got the other end tied to the scale itself, okay? And I've got a 0.5 kilogram mass hanging off of each end. So here's my question. When I lift that piece of paper up, what's going to be the reading on the scale? 0?
I don't know. How
Well,
it's-
what
I'm
is
gonna go
the
with
point
10.
of?
I don't know how it's oriented, like, is it measured?
Are these the same mass?
Yeah.
Yes. Both of those are 0.5 kilograms. Both of those are
So
0.5
doesn't that
kilograms.
side, what's it pulling on? It's just pulling on the.
Are there two separate?
It's
No,
not.
no, no.
Is it in the middle?
Yeah, so
I don't know what it
basically,
is. But
visualize this. I've got that string over there pulling this way.
On this knob,
Yes.
And
And
they're
then
both
I've
pulling on
got
the
this
same
one tied like this.
pulling on the same.
Yes.
So then it's 0.
So it's
zero.
like
It's
this.
0.
No,
Okay.
that's not how math works.
So one's pulling this way, right? Pulling that side. This side over here is just tied on pulling this way.
The 0 or the
It's
4.9?
10, isn't it?
I don't know.
Well, look, you're.
I know what it is.
Well, then you're lying to me. Why would
Oh,
you
no,
do
I'm
that?
just not telling you the answer.
I
There's a big
trusted you,
difference.
Burkham.
Get over it. Okay.
Reese's practicing to be a flasher.
No, it's gonna be like
Howie, your thoughts?
4.
So when it's on this side, pulling this way, it's
Wait.
reading that.
So it's not like, it's
It's
not like two
reading both of
springs.
them, right? It's not
Yeah.
just like tied to it.
It's like, so it's
Yeah,
one of the-
so it's like a tug of war. It's being pulled by both strings.
It's 4.9. You know what I believe?
I think it's
I
gonna
believe
be
that
like
Jesus
5.
is the one.
About 5,
He'll give you the answer.
okay?
I think it's 0.
It's
So there's basically, I've heard 3 options. I've heard 0, I've heard about 5, and I've heard 10.
-1.
Stop.
Those are 3 options. So how many vote? No.
What'd you say was the mass?
So both of them are 0.5 kilograms, okay? So basically, here are your options. 0, it's not reading anything. About 4.9, because it's a 0.5 kilogram mass on each side. Or it's going to be 10, because it's holding up both ways. So how many vote 0? 1, 2,
Joseph, I trust
Okay,
you.
2, 3,
I'll vote it.
5,
Oh,
6,
five.
Hey, on. Hey, mentality, everybody.
okay? About 5 people. How about 4.9?
That's me.
1, 2, 3, 4, 5,
Where do we
6, 7. Yeah, same weight on both
Yeah, but
sides.
this is.
I don't know what this is.
It's
Okay.
not.
I'm just gonna watch
That's not
TV.
how math works.
That doesn't pull.
8, okay? So,
That doesn't pull.
how many, so, how many vote 10?
Oh, yeah.
1, 10.
I knew I could trust you.
Yeah, you're wrong.
3, 4,
Was there
5. It's actually a pretty good
So it's not an actual spring on this side.
I don't think
It's
it
just
matters.
this.
It doesn't matter because it's pulling on the other
Oh,
side.
okay.
It's
Spring
still
on that
zero.
side.
No.
Yes,
it's
that's what I
zero.
said. I was like, it's just like this.
There's not a spring on the other side.
I'll make
Then
sure
it
it's
should.
zero.
Okay. All right.
I don't
So,
know what it's doing.
It's zero.
He did a science.
It's
yeah, it's about 4.9.
I thought it was like a double.
Ooh,
No,
yes.
even if it was a double spring, they'd both be reading 4.9.
Yeah, that's why I was confused. You said it was like the same thing.
Because here's the deal.
I told you guys.
What if, visualize this. What if I just hold this thing right here? This tension still has to be 4.9 newtons. So this thing is just acting like a wall, right? Now, here's the question. Could I pull this off if I had a 0.5 kilogram mass over there and a 1 kilogram mass over here?
Let's test it.
Let's do a science.
Well,
do
let's just put I'll put 200 grams
Go big or go home, Mr. Burkhamp. You have to
over there. Here, take that. Now I'm going to hold this and go ahead and hook that up.
Do a science.
No, what's the force?
Oh, there's no.
I just hooked it into it.
You got it, Liz.
Got it?
It was twisting on me.
Okay, so now we've got basically 700 grams over here and 500 grams over here. Now what's going to happen when I let go of it?
Oh.
Okay,
Our science fails.
right? So it immediately begins to accelerate. So this system accelerates. So what does that mean the net force does not equal? Zero. So here's the deal. If I wanted to, this is just basically what the vertical, this is basically an Atwood machine spread out between two pulleys. So if that's 700 grams, 0.7 kilograms, I could take 0.7 times 9.8 and call that my applied force. I got a 4.9 Newton force over here, right, because that's just 0.5 kilograms. So the difference between those two would be my net force. Now, how would I get the acceleration?
Divide by.
Divide by which mass? Both, because you always have to divide by the total mass of the system. Okay, so Liz, take that off if you would, please.
Do a science.
Okay. All right, so let's put that back in here. Okay. All right, now let's go over here. Here's what you can do on this lab. Lab itself is fairly simple. Thinking about it. Thinking about it. Hunter, focus. Okay. So you're going to take a 10-gram mass and you can hook that on the end of the string. Now, you need roughly about 70 centimeters to make this deal happen of string from here to here. So here's what I've got. I've got this cute little 10-gram mass hanging from the end. I've got a cart, I've got a 500-gram mass, I've got a 20-gram mass. So here's the question. Can that 10-gram mass accelerate this whole system?
Yes.
It's going to be 10 times 9.8.
You gotta
so
find
it should be accelerating
you gotta find
about.
the friction. It probably will.
We're assuming that it's a frictionless surface.
Oh yeah.
Okay?
for it.
Right? So I let go?
Wait, is this thing inclined? Because if so,
No,
it's cheating.
it's pretty flat.
Okay.
Okay, so here's the deal. So what's making the system accelerate?
Gravity.
Gravity. So if gravity is making it accelerate, is the acceleration 9.8 meters per second squared?
No, it's 98.
No.
Hunter,
It's canceled out from that.
Hunter, just don't even talk. Okay, so visualize this.
No, it's not going 9.8 meters in 1 second. Okay, I can see that. Be all the way to the freaking chalkboard by the time you stopped it.
His answer, not
Look.
mine.
It's the code
All right.
giving him superpowers.
Okay. Now, so here's the drill. let's just focus on the 10 gram mass. And Hunter, you do not get to answer this question. I want to find the gravitational pull acting on the 10 gram mass. So, Mr. Rollins, how am I going to take the 10 grams and figure out the gravitational pull acting on a 10 gram mass?
We're gonna multiply.
I actually know. Phone a friend.
Kendra, what am I going to do with the 10 grams?
Well, it's 10 grams, so you want to convert it to kilograms.
By doing what?
Dividing by 1,000.
And you get?
0.00, 0.01?
0.01.
Okay.
Right? And if I take 0.01 times 9.8, I get 0.098.
Okay, thank you.
Okay. So here's the deal. So acting down on this mass right now, there's a 0.098 Newton force pulling this thing down. If I cut the string, is there any opposing force?
No.
No. So therefore, without an opposing force, the net force is also 0.098 newtons. I take 0.098 newtons, I divide it by the mass, I get an acceleration of negative 9.8 meters per second squared. So if I cut the string, the acceleration is 9.8 meters per second squared because there is no opposing force, right?
Right.
And here's what's most important, is that not only is there not an opposing force, that force is only accelerating 10 grams. Now, by having the string attached to it, now when I let go of it, is that same force, and this is going to be the whole key to this lab, that same force, 0.098 newtons, isn't just accelerating that 10 gram mass. Now it's accelerating the 20 gram mass that's sitting up here, the 500 gram mass that's sitting up there, and the cart itself.
We should apply this to rockets.
What?
Like have a pulley and then lift up the rocket to shoot it up faster because it takes so much force to get it going.
That would be a train wreck.
That sounds like a pretty good idea, honestly.
I think we rocket wreck if you're gonna do that.
Okay, all right.
You should make a model.
Okay,
you know what?
good. Make it.
That's what Einstein proved never.
Yeah, they all told Einstein he was dumb too.
Yeah.
No.
Yeah, they did.
And he had his mom check his homework and his girlfriend check his homework. Yeah.
Look at that. Take that off.
Okay. Hey, all the best.
You're so strong.
So back to the question at hand.
Back to the question at hand.
You don't even have
So, here's the deal. So, what we're going to do is going to calculate two accelerations. A theoretical acceleration based upon this 10 gram mass that's going to accelerate this combined mass with it.
Do we need to find mass of this?
Yes, you do. So, let's talk about
What about
that.
the string?
So, the string is negligible. Okay, we're going to assume that the system is frictionless. So here's the deal. So I've got this cart by itself. How can I find the mass of the cart? And no, I'm not going to give you a gram scale.
Put it attached to a Newton thingamajig.
Yeah, hook it up to a Newton scale, get the reading in newtons. Then what are you going to do with the reading in newtons?
Divide it by 9.8.
Yeah, boom, there's your mass. So you got to take this by itself, hang it up, get a reading. Divide that by 9.8 meters per second squared. Boom, there you go.
Divide by negative now?
I haven't done this for a while, but I'm on the verge of stopping and just having you do the lab on your own and not answering any questions. Hunter, you have a choice. You either start paying attention or leave my room. I don't care what you do.
Okay.
You make the choice. But I'm tired of being distracted by that part of the room. Is that clear? All right. Now, why don't you teach freshmen? Because they act like that. Stop. All right. So you're going to do 5 trials with this. I don't care how far it goes, but it has to go 50 centimeters. So I don't care where you start. I don't care where you stop. It just has to travel 50 centimeters. The reason that we want 50 centimeters is because we're eventually going to calculate an experimental acceleration of this cart. To do that, we need the distance and we need the time. It makes it easier if you let the distance be 0.5 meters, because you're going to use x equals 1/2 at squared plus v naught time. If you're smart, which you are, what are you going to let the initial velocity be?
0.
0. Then you don't have to worry about that part of the equation. So you're going to measure the distance that it travels, which is going to be 0.5 meters. So start it at, 90, let it go all the way to 40. You just have to have a distance where it travels 50 centimeters without that weight hitting the ground. When you're stopping it, okay, have somebody timing it, but don't physically stop it at this point. Okay, let it go past where your 50 centimeter mark is, then stop it. Stop the timing when it crosses this point, but don't physically stop this until it gets to that point. Now, when you get done with that, you're going to take off the 10-gram mass, put it back up here, take the 20-gram mass, put it out here on the end. Now, what's going to happen to the acceleration? Should get bigger. But now, why do you think I put the 10-gram mass back up here? Close. Same amount of mass. That way the total mass of the system remains constant. So basically what we're doing is that we're letting gravity apply a very, very, very specific amount of force. I could do this by doing the same lab and me pushing it with my hand, but the problem is my hand can't really apply a constant force over 0.5 centimeters or 0.5 meters. So basically what we're doing is that we're letting gravity do the work. So by putting that out there on the end, with that same distance, we should get a bigger acceleration. So what should happen to the time?
Get shorter.
Yeah. So we're going to keep a whole bunch of things constant. We're going to go dink, let go of this. So here's what I want you to look at. This is basically Newton's second law of F equals ma. We're going to increase the force. We're going to keep the total mass constant. Therefore, as we increase the force, the acceleration should get bigger. Beautiful. Let's go back. So on page 1, this is where you're going to write down your data. You have the 10-gram mass, the 20-gram mass, 5 trials each. Take the average of the times. Then, on that 10-gram mass and that 20-gram mass, so let me go through this, make sure everybody knows where we're at. So what we're going to assume is that the system is frictionless. And we're going to assume that the only force available to accelerate the system is gravity pulling down on this 10-gram mass. So, we're going to take 10 grams, change that into kilograms, multiply that by 9.8 meters per second squared. Let's make sure everybody has this number. So somebody take 10, divide it by 1,000, and multiply it by 9.8.
0.098.
0.098. So on that 10-gram trial, we're going to assume that this is my applied force. We're going to assume that this is a frictionless surface, that there is no opposing force. So this is also my net force. Okay? Now,
Do we have to show the calculations for that, or is it just fine if you assume that we know?
how long have you been my student? Let's go with show the work. Now, to get your theoretical acceleration, you need the total accelerated mass. The total accelerated mass is going to be the 10-gram, the 20-gram, the 500-gram, and the mass of the cart itself. So up there at the top, the first thing that you have to do is find the mass of the cart. Then add that to the 10, the 20, and the 500. That becomes your total accelerated mass. That stays constant throughout the trials. Okay? That stays constant throughout the trials. So here's a common misconception. This thing is sitting up here on a flat surface initially. Don't think that, oh, the weight of this is an opposing force. Okay? This isn't an opposing force. Does it have mass? Yeah. Does it have inertia? Yeah. Does it want to remain at rest? Yeah, it does. Not denying that. But that's taken into account when we take force and divide it by the total mass to get the acceleration. So don't think this thing up here, because it's not a resistive force, it just wants to stay at rest, okay? Because it has a lot of mass and has inertia. So don't think this mass is an opposing force. We take that into account when we divide that net force by the total combined mass. Okay, so you're going to do that with the 10 gram, you're going to do that with the 20 gram. Now, over on page 2, you're going to find the final velocity using the theoretical uniform accelerations and the average time. So you're going to go, okay, hey, my acceleration was 0.5 meters per second squared, whatever it is. Multiply that by the average time. That's going to be your final velocity for the 10, the final velocity for the 20. Then, on line 2, you can determine the acceleration of the car based upon your measured values of displacement and time. So on number 2, you're going to calculate your experimental acceleration. Okay? That's what you're going to do at that point. That's when you're going to use, oh, right, x equals 1/2 at squared plus v naught time. Okay? That drops out because you started the car at 0. You know the distance, which is going to be 0.5 meters. You know the time. You're going to solve for that acceleration. So you're going to compare those, you're going to get your actual experimental accelerations from that. You're going to get your theoretical from this. So you're going to get your acceleration 2 different ways. One based upon distance and time, one by taking the net force and dividing it by the total mass. Okay. Now, then you've got some questions to answer. On page 3, this actually needs to be done as part of the lab as far as collecting your data goes. So what you're going to do on part 3, each of those stations back there, you've got a little block of wood. So what you're going to do on that part is that you're going to take, here's the table, you're going to put a little block of wood underneath it, and basically you're going to turn this thing into a pretty shallow inclined plane. You need to adjust that pulley so that string is still running parallel with the ramp. Okay? So this is going to be pulling down like this. Okay? And there's a couple of things that in an ideal situation how I want you to pay attention to the spirit of this. I want you to look at this and go, okay, right, first off, what are all the forces acting on the system? You're going to draw those in. If you think it's acting straight down, draw it straight down. If you think it's going parallel with it, draw it parallel. If you think it's going down, draw it that way. So what you're going to have, you draw the forces that you think are acting on the cart. Then the idea being is that you're going to predict, say, hey, what's going to happen to my acceleration? What's going to happen to my time? Then you're actually going to run the trials again, but you're going to use the 20 gram mass. Don't use the 10 gram. You're only going to run the 20 gram mass, and you're only going to run 3 trials. And then basically you're going to say, hey, this is what happened. Now, again, you're going to go back to what's going to happen to your applied force. Are there any forces opposing that motion? Okay? What's going to happen to your net force? That type of thing. Then over on page 10, or excuse me, number 10, on page 4, you've got a series of questions to answer. You've got a block suspended by a pulley. When you get to number 11, pay attention to number 11. What I want on number 11 is a generic equation I could use to find the acceleration of any system with a block sitting on a table that's frictionless and a weight hanging from the end of it. So you want to define your masses. Basically, you're going to have 2 different masses. You're going to have a mass that's suspended, and you're going to have a mass that's up on the table. That's it. Those are going to be your 2 masses. There's nothing else. But at some point, if you subtract the masses, if you add the masses, if you multiply the masses by something, just don't put, oh, I'm going to use mg. Well, which mass? Are you using the total mass? Are you using the masses hanging off the table? Are you using the mass that's up on the table? So you have to be very specific. So basically, when you get done with number 11, here's how you can check that your equation on number 11 works. Go back to page 1, where you're going to have known masses. Plug in your numbers from the 10 gram trial into what you think your equation is. See if you get that theoretical acceleration that you calculated on number 1. If it works, hey, you're golden. If it doesn't, it's bad. And if you're not sure if it works, when you get done with that equation, give it to one of your colleagues and go, hey, what I wrote, did this make sense? If it does, hey, you're golden. If it does, they look at it and go, I have no idea what you're talking about. Then something's probably wrong. Okay? All right, due on Monday. Go be free.